bot spam, not bot testing. There we go. Okay. How are we all doing today? A jaunty little tune. It's almost that time. Woo! Look at all them viewers. Oh, good. The bots did go to the right channel. I was concerned. I had it going to a secret channel. Didn't check my... Okay, good. Mic is working. It's Bluetooth off. Bluetooth off. Ha. Oh shit. Shoot. Class hasn't started. I can still curse, right? There we go. Howdy. How you doing? Hungover. Ooh. Birthday stream. Oh, that sounds fun. Any super clips that we need to watch in class here? I am 25. Ooh. You're a Smite streamer. Is Smite any good? Oh, I suppose we should get going. I never got into Smite, those jungling type games. What are those? It's the term for the Smite kind of game. It's escaping me right now. Like the League of Legends, Dota, all that fun stuff. Gaming addiction is real, boys. MOBA, thank you. I swear, I do know things. I promise. I tried League of Legends, and it was just too brutal for the griefing. So I started playing Rocket League. Yeah. They're fun. Yeah. People are mean as hell. It is bad. But good times, though. 25, congrats. It's a big honor. Now, let's see. What's left after 25? You get a reduction in your car insurance, and then you get to look forward to turning 40. Oh yeah, thanks for that survey. I forgot all about mentioning that. The survey, if you saw the announcement, the double announce, well, you didn't get the exam announcement yet. It's the other class that got like 2 announcements in a row. 26, and I don't get health insurance. Aw. Oh, I read your title backwards then. But yeah, so since this is my first year at GVSU, they do midterm feedback on all the new faculty here. Which is funny because this would be my 6th year of teaching in total. If we counted everything, but I'm new to Grand Valley, so that's fine. It's better than having people come into the classroom and sit there and eyeball you like you're doing something wrong. Come on, go over here. Thank you. Yeah, that is the next milestone. Right, where did we end? We ended here. Okay, so let's do some administrative talk. We'll do a bit of geometry. I highly doubt we're going to get through everything in here today. This is still pretty dense material, but I'm not planning on blackboarding today, so we should be all right. So, exam is on Thursday. Hopefully we are all remembering that that is coming up. What we're going to do is, let's see, at 5 or 4:45, we'll do a hard stop, and we'll look into the exam guide. So the questions that I put up on Blackboard for you all to check out. Feel free to ask any questions that you may have if there's anything you're struggling with for this particular set of questions. I read them, to me they seem reasonable, but I've also been looking at these questions for probably 3 years now. So if you're unsure about, don't hesitate to ask when we get to that part. Otherwise, I'll probably handpick a few to talk about. I'll ask you, what the answer is. I'll stare at you blankly until somebody answers me, as is tradition with teachers, where it's what we're supposed to do. And yeah, that'll be about it. So the format of the exam, just to, I guess, contextualize it or to at least set it straight. You have a 24-hour window to take the exam. So I will open it up on Thursday morning at midnight. I will close it Thursday evening at 11:59. So basically, you have a full 24 hours to take it. Feel free to take it from 4 to 5:15 if that's going to be good for you mentally to do it at the same time. You could start it at 9 a.m. and finish it at 6 p.m. Just make sure that you have it submitted before 11:59 because that's a hard cutoff. There is no timer on the exam, so if it takes you 6 hours to get done, that's your call. The intent is to be flexible because I know with technology and doing things online, it doesn't always work out the way we hope. Only consideration and concern is, again, read that big block of note text. No Respondus browser, no proctoring software, no locking down your computers, no ridiculous privacy violations on your part. In return, just please don't plagiarize, please don't cheat. That'll be our agreement for that. And if it's any consolation, we just sat through a good hour-long talk on the university's new plagiarism and cheating policy, and I don't know quite how I feel about it yet. Um, Basically, there is a new division for handling academic misconduct, and it seems to be interesting. Basically, if there's any plagiarism or cheating that's detected, it automatically goes to a department. Yeah. In the past, you could kind of work it out with your faculty member, unless it was really blatant. But if I detect cheating and it's pretty clear, like there's no wiggle room, it's a legal thing now. It's part of your student code. They actually wrote it in there. So it's stressful for everybody. Again, just let's not get into that. If you can, please do that for me. I think I hate it worse than you guys do. And it sounds like it's the end of the world for everybody, but yeah, let's just not do it. Okay, so we'll talk about that at 4:45. Maybe a little bit closer since we're already getting into it. Um, right, so we will get into geometry, and I want to kind of get through some of this. Now, this set of slides is not going to be on your exam, by the way, since we're not all the way through it, so you don't have to worry about geometry and transforms really on the exam. I'm not going to ask you about matrix math and things of that, since we're not really getting into the meat of it until today and probably Tuesday. Oh, that was the other thing I forgot to mention. I did want to say it. There will be no class session on Thursday. So I won't stream, there won't be a Zoom, it'll just be your time to take the exam. So that you're not like stressed about being double booked or anything. If you do have questions, please feel free to message me on Discord, email me. Worst case, we can do a quick video call if you need or something like that. But yeah, hopefully it won't be too bad. Anyway, we ended here. We were talking about model view projection transformations, right? So we kind of were talking about how everything is going to have a frame that we have it centered on. So every object, every point, every vector will be set in a frame. That will be basically specified by a point and then a vector, or basically a set of homogeneous coordinates. It's going to be your 4x4 matrix that we were talking about. Right? And if we want to say rotate something, we're just rotating its frame. If we want to translate it, which means move it, we're moving its frame. That's basically what we're doing here. Again, getting a little bit more into math just to set the basis for this. Again, you're going to be using libraries for all the matrix math and all the vector math. You don't have to know how to do this. It's helpful, if you do want to go really deep into the nitty-gritty of graphics, it's great to know the details. But for me, just using what is available is going to just streamline the whole process. And you could take that argument, why don't we just use Unity? And I would say you have to have some basis here. But anyway, so we left off talking about these different spaces that we're going to have. Right, so we're going to start off with our local frame. We can transition that into a world frame. So we're going to have a local basic space. We're going to apply a model matrix. Now we are in the world frame. We will apply a view matrix. We are now in the view frame or the view space. Let's do a projection. Now we're going to get into our clip space where things that don't need to be seen or that should be seen are now rendered. All right, so you can see here we are top down and then we go to kind of an isometric view. Then we'll do another transform. You don't see a matrix here, but this is basically going to be aligning with whatever API you're using. Let's make it viewable on the screen. So here you kind of see, maybe for example, this would be like our WebGL drawing space. So you see the origin is centered here. Now the origin is centered down here. If you flipped it around, it'd be up here for like a standard viewport. But what we're getting at is that we have all these matrices we're applying. So you define a cube, and to get from here to here, there is a minimum of 3 matrix multiplications happening. All right, so we're going to multiply the model, the view, and the projection matrices together. We'll apply it to our object, and then we have our screen. Pretty trivial, honestly. Now, to go back to a little bit of the symbolic math here, anything is going to be represented in the same format. So we're going to have a frame that is represented, kind of looks like this. So these are basically just going to be 4x4 matrices. This is a shorthand way of writing it out. Oops, going the wrong way here. The important thing is this last entry. So this will be your homogeneous point. So if it is 0, it's going to be a vector. If it's 1, it's going to be a point. We are more than likely going to be using 1 for everything because we're dealing with, we're dealing with points, we're dealing with pixels on a screen. So we're going to be leaving this pretty much as 1. Now we can do some fun stuff with this particular parameter. If we change it, you're going to get into like perspective scaling, things of that nature. We'll get to that, don't worry. So let's say that we have 2 frames here, and you can consider these 2 frames A and B. So you had that standard 3-dimensional axis from a few slides ago, and then the second one could be the frame that is slightly rotated. Okay. If we want to transition from B to A, let's apply some random matrix M, and since we're doing a rotation, it would be a rotational matrix. And then you say, what's a rotational matrix? Well, it's just set up so that all of the points are going to be rotated. So if you remember that spinning square you had, you were applying your sines and your cosines to the points, right? We're just doing the same thing, except we're filling out a 4x4 matrix instead of a XY point in, in your shaders. So just for terminology's sake, this is an affine transformation. So if you need to know what this is to look up later on, if you're Googling transforms, this is an affine, meaning that we have a point and we have a vector. Right? If we didn't have it, it would just be a basis. Like it would be a frame with no basis, no origin. So let's actually talk about now all of these other transforms. We have 4 kind of basic ones. We have rotation, we have translation, we have scaling, and then we have shearing. We'll talk about all of these. Shearing is where you would like have a square and you try to pull it apart. So it kind of becomes a parallelogram type of thing. Excuse me, I seem to have a frog in my throat. All right. Don't know how streamers talk for hours and hours without killing their vocal cords. I was recording some lectures earlier and it's a lot. Anyway, you don't care about that. So if we want to do any of these transforms, we are changing our frame. Again, we are basically updating this 4x4 matrix. How do we update it? Do some matrix math. Do matrix multiplication, basically. Something that you might be concerned with, and you may or may not be at this point, you have 12 degrees of freedom with a affine transformation. So basically, for every axis, you can do a certain number of things to it. Basically, this is just kind of a combinatorial notion of the fact that we have a 4x4 matrix that we can do stuff with. We have 12 degrees of freedom. So if you have, like I'm going to do this weird little right-hand rule type of thing, right? We have our axes going in basically, kind of perpendicular directions. We can only update based on these three axes, right? So if we're going to rotate around Z or Y or X, you can't go beyond to some crazy extra orientation. You're limited by reality in a way. Um, think of it like pitch, yaw, and or yaw, pitch, and roll if you're doing any kind of aircraft simulation, or if you've ever taken like a robotics class, the joints can only move in certain ways, right? They have X degrees of freedom. Same thing here. That's kind of the general idea. It's just how we kind of shift things and move things around. So moving on, in that kind of flow chart that I showed you earlier about going from frame to frame to frame, you saw the world and the camera frames. Basically, these are going to be what your environment comprises. So the world frame is going to have everything centered around some origin. Right, again, we have every object has their own frame. These are going to live in a world, which intuitively makes sense. But these objects that we have in this world frame are going to be all positioned in relation to some origin point. Again, it makes intuitive sense. Let me grab a couple of things here. So here's no, let's make this fun. Let's grab my little friends here. Okay. So I've got Kirby and I've got Link. Say hi, Link. Hi. Kirby has his own frame. Link has his own frame. They each have their own origin, right? If we start rotating them, they rotate about their own origin. Now, we apply a matrix multiplication to move this into the world space. Let me go back here. So we are now in this world space, right? If we transition them to this particular context and I start rotating them again, they're going to do this. Okay? So now they're centered around some origin point. Let's apply another matrix. So you see your view matrix here. Now we're in our view space. Instead of looking at them like this and they're rotating, well, the camera has now moved such that we're looking at their heads, looking top down. And we could still be doing like this kind of a thing with rotation, but your view has changed. Then you go to your clip space. Maybe Link is not shown. He's been clipped out. And we kind of rotate Kirby slightly so you can see his cute little face. Oh, look at that. All right, I've been spending too much time with kids today, I see. Basically, the point is that these frames are going to change your perspective and they're going to change what you are doing in relation to some origin point. Now in OpenGL and WebGL, your basic frame is your world frame. Can I ask a question in voice chat? Yes, I think I am in the voice chat channel. And sorry, one sec, I can't hear you for some reason. There we go. Okay. Good. Yeah, go ahead. Yeah, so back to the slide here. Correct. So the yeah. Yeah, and just let me do a double check here. Nobody else could hear Noah, right? In Twitch? Because if you can, that's problematic. No, okay. Okay, good. I intentionally set it up that way, but I just want to make sure. So yeah, the question was applying the model matrix to some objects. We'll take it from local to the world perspective, the world space. Is that your question? Okay. So yes, that's correct. So basically you're going to define some object, and here you have a cube. In our WebGL framework, we call them, there's like a quad function that basically allows you to define squares easily. you're going to multiply all these vertices by some matrix, which we'll define as a model matrix, and it will take you to that different origin, basically, yes. Different frame. Yep, so you got that right. Yes. Yeah. And well, it may, so you may have to apply like a translation or something like that. So the other question was, is it going to put you in the correct place in the world? So it should, yes. Yeah, so I get your question. So basically in WebGL, it's going to change what we're seeing. So it's going to reorient the scene to whatever perspective you want. So you could do top down like you see here, and it'll move the camera, which by default is looking at kind of your top down world here. You could turn this into an isometric view, or you could turn it into some kind of perspective or orthographic or whatever you want. Just depends on what view you're looking for. So yeah, it will basically change what you're seeing based on a camera. Camera. Uh, Yeah, yeah. So there's the question for those of you sitting in Twitch having no idea what's going on. Um, so there's a game where the ground moved instead of the camera, basically, right? Hmm. Yeah, so you can do whatever you want. You can move the camera or you can move objects. So we can translate objects around without moving the camera, and we can move the camera without transitioning objects. Just kind of depends on what you're going for. There are pros and cons to both, basically. We're weep from notes. Yeah, sure, no problem. Yeah, and there you go. There's one way to have voice chat. Not too bad. Um, but yeah, so basically, we're going to be moving things around depending on what we want to show the user. You can have objects moving, you can get them out of clip space, you can change perspective with the camera. It's going to be up to you. We can translate whatever we want and rotate and move things. Yep. So, where were we here? Okay, so the basic frame is the world frame in OpenGL and WebGL. So we're going to define our objects here. And then this is basically going to be kind of our default starting spots. Depending on your API, you might have different perspectives that you start with. And that's just going to inform what your matrices that you build up are. Okay, so we'll call this m equals I. So basically m is your identity frame. This m is basically, it's going to be a catch-all for our transformation here that we're applying. So first thing we can look at here is let's move the camera. So let's say that we have a default world space, right? So we have a cube, we have a rectangular, I guess it'd be a rectangular prism, but 3D rectangle. We have a circle, we have an ellipse, these are probably spheres of some kind. And our camera is sitting at 0, 0, 0 world space. We have a nice old-timey camera to represent this. If you want to see everything, you're going to have to move the camera, or you're going to have to move the objects, one of the two, right? An easy way here, let's just translate the camera. Okay, then everything doesn't have to move in the world. We don't have to do a loop over every single object. We can just shift the camera frame, and then it's one operation versus four here. So that's one way you could kind of handle perspective, basically. And what does that mean for us? Well, we would basically define our matrix here, M. So it's an identity matrix. So 1, 1, 1, 1, diagonally down the line here. And then negative D for this fourth column is going to translate us on the z-axis. Okay, and we're going to get into how to build up these matrices and how to apply them, basically. Now, you see here, we are finally kind of in the context that we'll be looking at for this class. Negative D is going to bring us towards, like, away from your screen. So if I've got a camera here, I've got my little camera, and I want to move it in a negative direction, I'm pulling it back this way. Everything in the scene is going to get smaller, but maybe we have objects go into our clipping volume and we can now see them. And what do we do with this M? Well, we just multiply our current matrix. We'll call it a current transformation matrix later on when we get to that point. Basically, kind of the key takeaway here is that all of these operations have a well-defined construct. So if you want translation, do this. If you want rotation, do this. There's not a lot of ambiguity there. It's kind of easy to just have like a little lookup table. Okay, if I want to move this thing around, okay, it's this type of matrix. If I want to rotate it, okay, the cotangent goes here, or the cosine goes here. It's pretty rote memorization almost, but you'd have a lookup table for that kind of thing. You don't have to memorize it. So this is kind of an example of what Noah was talking about here as well. Nice little perspective. Here we see the camera moving, right? So this would be one way to have an object move around a scene. Let's just kind of shift the camera, shift our duck, and this is what we saw last time. They're moving in lockstep, right? So maybe if this ground here is fixed, we have this illusion of motion. What Noah was saying was that in this game, they were moving the ground plane. And there is nothing wrong with basically having, a large object defined for the bottom, or, maybe a bunch of them if you're doing something like a procedural type of thing. Have that ground plane shift, leave the duck at the origin, and it looks like it's moving. There was a Zelda game that did that now that I think of it. I don't remember which one it was. But that is one of the tricks that you can do. Have all the environment be the things that move, and your player just sits at 0, 0, and he or she never moves. Maybe the animations run, but you never leave that point. Meaning that your character never like goes out of memory or out of bounds or something like that. Okay, so enough of well, we're not leaving the realm of theory yet, but let's talk about some transforms and how we can actually create them. So our standards are rotation, translation, scaling, and shear. Now these first three hopefully make sense. Rotate about some axis. All right, so rotate around Y, rotate around X, rotate around Z. Standard rotation. Translation, move from one point to another. Scaling, get bigger, get smaller. Shear is kind of the interesting one, and this is going to involve that whole cotangent thing that I was talking about. But if you're shearing in a particular direction, you might start with a square, and then you shear by some angle. So now you see here we have like a, let me get my little pointer here. You have an angle being defined for all these points, right? These lines don't change. These are the same length, right? So same thing here. This would be an X shear. These are the same, but these are now at a slightly different angle. So that's just what shear means. Standard transforms, they're useful for all kinds of things. Again, just basic coordinate transforms. And what is a coordinate transform? That is just applying one of these transformation matrices. I keep saying applying them. I'll show you what I mean very soon. One thing of note here too is that we are only really applying these transforms to points. All right, so we talked about vectors before, and kind of what it means to have a vector in the space. But at the end of the day, we're kind of dealing with vertices. So what we are going to do in WebGL land is we are going to say, define what vertices we need, apply a transform, and then we're going to let WebGL handle all the line drawing. Okay, so you only have to care about the standard endpoints, and you've seen this already. You move those triangles around the screen, right? You started rotating that square. You played with the Sierpinski gasket. You only defined the points, right? You didn't say define the shading for a triangle face. You didn't define what the lines are between points. For all you cared, when you were clicking that gasket around, you clicked here, it was standard. You click over here, now it's this weirdly scaled, kind of object, but you didn't tell it to redraw the lines. It did that natively. That's one of the nice benefits of using a library or an API of some kind. So implementation will handle that. Kind of the key here is that if we have a funky line kind of like this, so we have a spline basically, starting at point P, and maybe P is the only thing that we care about definition-wise. Maybe this vector here is important for this spline. If I want to translate it to be this particular type of line, I apply some transform. P becomes Q. Okay, so this vector is important for this example because this is going to define the basis over here. But I define Q and I give it some information about this vector, and the line automatically draws itself in this particular fashion. Okay, so I'm not telling WebGL, okay, draw a cute little squiggly line. I'm saying point here, vector here, you do the work. All right, so how does this fit in with our pipeline? Because we talked about the pipeline. The pipeline is one of your exam questions, by the way. Transforms fit very nicely in our pipeline. So we have a very messy looking figure here. You see your rasterizer. So this is basically, kind of right by the fragment shader, right? So let's say we have a list of vertices. Okay, so we've got V and we've got U, two random vertices. Could be that we're drawing a line between them or they're just points. At the end here we have a red line, so let's assume there's a line here. I apply some transformation to the list of vertices for this application. Okay, so think back to all the things that you've done so far. You have that list of vertices that you pass to the vertex shader, right? Then that gets sent to the fragment shader where it's colored, and then it gets drawn nicely on your screen. There is a step, and this will typically be done in the vertex shader for positional types of things, where we can apply a transform. Now we could do this in the application, could do it in a shader, depends on what you want to do. The hint, if we're doing matrix math, it should probably be in the shader so the GPU can handle it. But you're going to transform these matrices. And again, a transformation is just matrix multiplication for us. We have a generic transform, T. Okay, if we are shifting V to U to U to V like this, it's probably a, it kind of looks like we have a rotation happening. So if we have an orientation like this, and now it's like this, we could have a rotation and a scaling factor if these are grouped, or maybe it's just a translation, meaning it goes from this point to this point. Just kind of depends on what you're drawing here, right? But this transform gets applied to your vertices, and then it gets sent to the rasterizer, which doesn't care. I mean, it's just taking in points, and it's going to apply, build up fragments. It's going to take in your colors and your textures and whatever you've done and tell the GPU how to render it. Make sense so far? Again, transforms are not crazy. There is a ton of math underneath it, but it's kind of foundational math that we're just going to apply at this point. But we have basically transformation matrices going in here. Okay. Now you might be concerned about notation if you're not asleep already. You're probably not. But kind of the thing here is that we're jumping between notations, and that's kind of why I have this slide. Everything is technically coordinate free. We're not saying, This is Cartesian or polar or any of the other coordinate systems. It's being defined by you, okay? And that's going to be based on your frames that you're building up when we initialize our programs. For discussion purposes, uppercase letters, we're going to make points. Lowercase letters, vectors. Greek letters are going to be scalars here. So we have alpha, beta, and gamma here. If they're bold, they're going to be representations, which means that they're basically a list or a four scalar array. And this just means that we are going to end up with a 4x4 matrix, basically. So just brief point of notation. If it's confusing, we're just defining how we're going to represent these things. Effectively, everything's a 4x4 matrix from this point on. So first one, translation. So we got about 10-ish minutes before we start talking exams, so it should be enough to get through the basics here. Oh God, it's so loud in my ears. I turned my volume way up to talk in chat, and then need to just sign out of Outlook mail or Office mail or whatever that awful thing's called. Okay, translation. We are moving a point to a new location. And this can be a list of points that all get moved to a new location. Right, so we'll consider it a displacement. It can move along whichever axis you want. Basically, we have 3 degrees of freedom. Move in X, move in Y, move in Z. Okay. So here we would see, if we were considering this to be a 2-dimensional object, we have go over this much in X, go up this much in Y. And then the displacement would be length D. Notation, P plus D equals P prime. Should make sense. I feel like I'm doing lots of talking over what linear algebra basically is. All we're doing is moving a point, so you could consider your slope or however you want to think of it. But you're moving in X, moving in Y, that is translation. We can throw in Z pretty easily here too and have it come out the screen or go into the screen. Now the interesting thing here though is that, so we have some nice clip art from the textbook. Let's say we have an object here, right? So here is a cube. Every face on the cube has some texture that's been applied. When we get into, I think, Blender, we'll talk about like UV mapping and all that kind of fun stuff for putting faces on objects. But we've basically defined, the points of this particular object, right? So we're defining the vertices. If we are applying a translation matrix, meaning that we're displacing points, we are just moving every vertex that same amount. Okay, so if we are doing P plus D equals P prime, extending that to a 3D object, we're just moving every single vertex by D. Okay, so we're shifting it. We're not caring about the lines in between. We're not caring about the faces, the beautiful textures on here. We're just moving points. Fragment Shader can handle the rendering. All right, so we're getting towards the whole 4D matrix here. Since we are in 3D, we're going to call P, X, Y, Z, and 1, because again, we need that homogeneous point. P prime, it's going to be X prime, Y prime, Z prime, and 1. Again, these are points. D, which is our displacement, we're going to call dx, dy, dz, and then 0. And this is where the vector and the points come into play. So basically by doing something like this, we're saying take this points array, apply a vector of displacement, and then the new location is going to be all of those parameters prime. So all this is really saying is that add dx to x, add dy to y, add dz to z. There's your new spot. These are transposed because, again, we need our column major format. But basically, it is something that looks kind of like this. And this is finally, after a lecture and a half, we've gotten to the actual matrix multiplication. I told you there's a little bit of theory here. Kirby apologizes. But you're creating an identity matrix. Let me step back for a second here. We're building up this transformation matrix. Okay, so transformation is going to be all of whatever we're doing is one matrix at the end. If we are starting it out as a translation matrix, we are basically defining an identity. So 1, 1, 1, 1, everything else zeros. Oops, going too far. What is the bottom row again? This one. Okay. It's just rounding it out to be a square matrix. So we need a 4x4 for all the matrix math to work out. The important one is basically this bottom right here. Yeah, because there's very specific matrix math rules, right? You can't do x by y times z by 5 type of matrix, otherwise it doesn't work. Yeah, don't feel bad. Matrix math isn't my strong point either, if you haven't guessed that yet. Intentionally glossing over some details, but you don't necessarily need to know all of it. Anyway, so here's our transform matrix. dx, dy, dz. This is going to be that fourth column in this 4x4 matrix. We're going to have this point be a 1 here in our matrix, and we're going to take this and multiply it by whatever our vector, or sorry, whatever our vertex matrix is. So if I have a matrix of points, basically defining this object, and I multiply it by this translate matrix, it's going to move those points. Every single affine transform, and again, affine means we're going to be doing something with a vector and something with a point. Every single one of them can be handled this way, which is why graphics cards and matrix math go so well together, because we can pretty much do everything we need to do to manipulate objects in space in a 4x4 matrix. And the other really nice thing is that we can concatenate these transforms together. So we could do translation times rotation times translation times rotation times translation times rotation times shear times scale, and they all collapse down into a single transformation, which we apply to our object. So we don't have to do this one at a time. This can all happen at once, which is where the power really comes in. All right, so let's see, how many more? We'll probably get through rotation, then I'll do a hard stop here. So this is our first one. This is why I said these are basically, simple lookup tables to do something. Anytime you want to translate something, this is what you're doing. It's not going to be really all that different. dx, dy, dz. How much you want it to move in x, how much in y, how much in z. Apply this matrix. And this is something that you can even predefine too. Now, rotation you have done, right? So you did some rotation before. If you want to do it in 2D, we have formulas for that, right? So if we have a point xy here, and we want to move it to xy prime, well, we can define the overall formula here as x prime is x cosine theta minus y sine theta, right? So we can basically figure out what the actual formulas are for rotation as well. Again, we've talked about this a little bit in the past. I don't care if you memorize the rotational formulas or not, but the point is that we know how to rotate things. Take this formula, stick it in a matrix, you have rotation. This is one of those things that you can look up, and if I asked you to do it on an exam, I would provide you the formula, so you don't have to freak out about that. But again, basically we have a notion here, and this is in 2D, right? So we are rotating about the origin in this case. But if we want to add in z, there's no difference, okay? Except that we have a third dimension to deal with. So let me show you the matrix, because this will actually help illuminate or give you an idea here. Basically, when we move to rotation in 3D, you're just rotating about some axis, right? So before we were rotating about the origin, depending on what we're going to be doing, typically we'll rotate around the origin. In 3D, we're going to rotate around some axis. You're rotating around x, rotating around y, rotating around z. It just kind of depends. So here, I guess let me step back really quickly here, because this example on the slide you might get confused if it's not contextualized. So if we are doing this rotation, sorry, if we want to do this rotation in 3D, is kind of the point, nothing changes. So 2D rotation, 3D rotation of the same type, basically Z is fixed. Okay? So in this case, we are not changing Z at all. All right, so in this case, if we're defining our rotational matrix, rotating about the z-axis, which you kind of see, it'd be something like this, right? So we're rotating like this guy. Our z-coordinate is fixed at 1, and then we just plug in our formulas, cosine theta minus sine theta, right? X cosine theta minus y sine theta, x cosine theta minus y sine theta, x sine theta plus cosine theta, x sine theta minus y. I think I'm missing a negative there, but uh, just hand typed in. That's the issue there. But basically, we have our x, we have our y, we have our z, x, y, z. Go back here. Not necessarily as easy to see in this particular matrix, but again, these are just well-defined, well-known matrices to fill in. This would be rotating around the z-axis. If we wanted to do this around the y-axis, we would fix the y-coordinate and move our rotations to the z. So basically, I've got this right here, which is good. Rotate about x, we don't change x. We move our formulas down here. Rotate about y, we leave our y fixed. We move x cosine theta plus sine z sine theta. Basically, the key takeaway here is that, again, theta is going to be something that you probably get from your application. If you're updating like theta every frame or something like that, you define your matrix in your shader, plug in theta. It's just going to rotate by merit of matrix wizardry. And then, scaling, we'll end with this one. Scaling is the same thing. So if you want to make something bigger, make it smaller, stretch it out, whatever you want, you just basically do this kind of identity matrix here, except instead of 1, put your scale factor in for each dimension that you are scaling. So if you want to make it bigger in x, make sx larger than 1. If you want to make it shorter in y, make sy less than 1. All right. Questions so far? Let's see, because if yeah, we'll end with reflection. Questions on this, because I want to give you a few minutes to talk about the exam. So if we're good with that, what we're gonna do for next week, Tuesday, is we're gonna wrap this stuff up. Towards the end, we're gonna get into Euler angles and quaternions. I don't know if I will play the whole video because it's a 12-minute video in class. It's kind of long. I've got the link at the very end of the slides here. So it's this YouTube video. Because quaternions are kind of interesting to visualize. This video is awesome for explaining what they are. So I've got it at the end. If you are bored and looking for a 12-minute video to pop on. Right, let's talk about the midterm then. So again, please read the note very, very carefully. I have to keep repeating that because of past students, not because of all of you. But let me start off with, does anybody have any pressing questions that they didn't understand with this? If you haven't seen this, again, it's in the exams tab or menu item, I guess. Yeah, sure, go ahead. So I've got some Discord. Yeah, can you hear me? Okay. We've got some voice chatter in Discord. Okay. Um, okay. So the question is, what is a pass-through shader? Does anybody in the Twitch chat want to take a stab at that one? So I guess let me maybe set the stage. If we were in class, we would have the half hour where I would just ask you questions. But anybody want to try explaining a pass-through shader? Looks like maybe Philip is. Kind of like Kirby and Link right here. It's a shader that just takes in the incoming values and returns them. Yep, so there you go. Basically, your pass-through shaders are not, your shaders are not doing anything other than passing the vertex and passing the fragment through. Yep, yep, exactly right. So if we were to go to, say, chapter 2 here, even, I think CAD 1 had it. So let's look at the source shader. Yeah, so this would be a pass-through shader right here. So there's your vertex, here's your fragment. They're not doing anything other than passing the raw values from application into GPU. I just realized I wasn't sending my voice to Discord chat as well, so you're probably going to get a late response. Make sense, though? Yes. Okay, good. All right, you said you had like 5 questions, so go right ahead. If you have questions, I'm going to guarantee other people probably have the same ones too, so. Yeah, sure. So, wow, keep forgetting to not click in the correct area in Discord because I've got a key binding for talking in it. So the question is, I guess, what does this question actually mean for WebGL? So let me give you a hint maybe, and somebody in chat can probably answer it too if they want. Standard OpenGL is going to have different concerns with frames per second than WebGL does because of the browser, and I'm curious if anybody can, if that question is clear, I guess. There's some extra overhead, I guess, if that makes sense. It's trying to be cute without giving away the answer. Any guesses? Okay, I'm seeing radio silence in the chat, and I just scrolled away, so... Okay. Oops. Too many things to click on. Okay. Oh my god, and then I clicked off of this. Okay, son of a bitch. See, I've got shift space as my push to talk, and it scrolls everything. Um, so in the browser, when we are doing WebGL, the browser's doing a bunch of other stuff. If we don't move, you can't see us. um, So basically, a normal OpenGL program or an SDL program or any other library is just dealing with that API and that application. Whereas the browser, it's doing a whole bunch of other things, including dealing with other tabs. It's dealing with your system, it's rendering the web page. Basically, you have a lot of extra overhead to deal with. If that makes sense. It's going to take a little bit more on your system than a straight up OpenGL program would. Another thing too with WebGL is it's based on the embedded OpenGL. It's not the standard plain web or plain OpenGL. So it's a little bit limited in what it can do. I just realized while I'm waiting for the next question, if that makes sense, I guess. So when I'm done with coffee for the day, I'll make like a hot water and honey and cumin. Or oh, awesome. This is basically a virgin hot toddy. I just realized that I make for soothing my throat. Needs a little bit of whiskey. All right, next question. Whiskey comes after class. Sure. So this question goes towards how we handle events. There are two ways to handle them. I don't even want to hear that word. Oh, did you have a rough night? Hey, Philip said he fixed you. He knows bio. So anybody want to take a stab at this one? So request-based and event-based. Two flip sides for handling, say, keyboard or mouse input. Very specific ways of handling it, though. Rougher day. It's any consolation, when you get older, your hangovers will start to last 3 to 4 days. Okay, not either I'm delayed or event-based. Okay, thank you. Kind of. Event-based when something happens on the screen, so the input comes from within the program. Not quite. So I'm glad we're talking about this one. So, event, massive oof. One always, yeah, exactly. So request-based means that you are constantly asking for input. So every single loop of your forever loop or your graphics loop, you're basically checking to see if an event has happened. Whereas event-based, you trigger a callback function whenever something happens. So if I click a key on my keyboard and it's event-based, I go to a callback function and I handle that key. Whereas a more classical approach, like a request-based, I'll have a function every iteration of the loop to see if there's anything ready to handle. There's pros and cons to either way, honestly. The event-based input is really well positioned in like a WebGL type of thing because you already have JavaScript callback events, right, that you can use. Um, Standard, like basic, and I'm going to go with like older style graphics programming, you would typically poll to see if there's anything in your event queue. Depends on what you're using, what you want to get out of it. So for those of you in the Twitch chat and haven't jumped into the Discord, Chris is feeling bad about monopolizing the question. So if anybody else wants to jump in, you're welcome to. Otherwise, he's got a few more. In which case, don't feel bad about asking them, Chris. Good question. So basically, um, Chris was asking about this one. Is it request anim frame? Is it set interval? The other one you might bring up is set timeout. Basically, you want to recursively or I guess call draw arrays multiple times somehow, right? You could do it recursively or in a loop. Excuse me. Um, yes, they're all correct. So like I said, we have looked at a couple of different approaches, and depending on your perspective, depending on which source you look at, some people will say use request anim frame all the time. That's better for performance. Some people will say use set interval, some people use set timeout. It's going to depend on your browser, it's going to depend on a multitude of factors, but yes, basically you want to have some method of calling draw arrays. We've handled it with request anim frame to call render. We've also used set interval to call render and try to lock it to a frames per second. As long as it's being called multiple times, that's triggering your buffer flip. Actually, request anim frame will natively trigger that buffer flip. Hmm. Ooh, good. Okay. So the question was, the only reason that can be thought of why you need a web server is so that I can access them. There is a very specific technical reason why you need a web browser. And rather than play the waiting game for you all, um, not to be negative, it's just with the delay. You need it to be able to load files. Okay, so we haven't gotten to that part yet, but if you want to load in models, if you want to load in any kind of scripts or shader code, you need a web server. Otherwise, it is considered a cross-site scripting attack, and your browser will forbid it. Let's see here. I wonder if I can do something quick and not look horrible. So let me Babylon JS playground, no sandbox. That makes sense, Chris? Okay. Now, got an ancient version of Blender on at this point. Yes, awesome. Yeah, if anybody else has questions, feel free to pop them on. Um, oh God, it's been. I have to refresh myself on Blender to be quite honest. It's been a while. I want. Shoot. This might just be a cube. Let's make it a wide boy here. Oh no. Wanted my monkey. I'm out of questions. Yeah, I should have a few minutes after class to chat. So the other thing too is that I've got I've got a technical question for you all as well. I think I actually have two, but let's see, it was a pentagon, right? So I will give you some boilerplate code, um, but basically I want to know how you would draw a pentagon, and I will try to run it. And I will probably make it something other than a pentagon, but it will be very similar. So don't like freak out if you see draw a rhombus or draw a diamond or something like that. It's all going to be the same, right? You just have to figure out where the vertices go. But I'm looking for a little bit of technicality here. If you can draw the squares, you should have no problem. But import. No. Damn it. I want a monkey. Where's the monkey? There's a way to do it, and it's been too long. Anyway, we'll just export this. So this is going to come out as a GLTF file. Let's drop it on our desktop. This is back to the web server question, by the way. So I now have an object, and got my exported model. Okay, so this is the Babylon JS sandbox, which is super cool if you get into modeling and you want to Blender modeling, and you want to see what your objects look like in a WebGL context. So Babylon JS is one of the other frameworks we'll look at after the exam, after we kind of get through the basics of graphics. You could do this yourself, like you don't need the sandbox. You can import models in WebGL, but you can't do it without a web server. Okay, so that's kind of the key points here. If I want to load in a model file, so here you can see my desktop, I've got this untitled.gltf. I could not load this in without a web server because it doesn't allow that kind of, it's basically considers it a scripting attack because it's coming from a different domain. But sandbox is fun to play with. All right, any other questions from the Twitch chat? I swear there was just an insert. Add, here it is. Okay. I knew it was in here somewhere. Monkey. There we go. Okay. No, go away. Go away, Cube. Nobody likes you. Monkey. Oh, he's got a face now. This wasn't there before. When did that happen? Export. Okay. I know, I'm just... The cube is a much maligned creation. There's a lot you can do with that cube. Refresh. Hey. Oh, did that... I wonder if I did the wrong thing. Oh, it's a... Why is it GLB? I exported it wrong. So this is a 3D object. I'm not sure why it's like a 2D texture. I must have done something wrong. Oh, I did grease pencil. That's why. There we go. There's Suzanne. We are not doing that right now. Okay. So there's our monkey. Whee! And I am not going to remember where the... I like Blender, but its UI is a bit... takes a bit to get used to. But we're going to be setting Suzanne on fire later on, don't worry. GLTF. Export. And let's... There we go. Ooh, look at that. A nice light source. Can I edit? Oh, you can edit. Neat. We'll be getting to this, don't worry. Whee! Blender is super cool if you've never played with it. It's open source, it's free, and it's a nifty little modeling tool. Okay, are we all good for questions then? Because if we're all good, I'll probably end the session a couple minutes early. Didn't quite get here. This is when we talk about translations and quaternions and that kind of fun stuff. I can show you the code quickly though, I suppose. for this one. So here we have a spinny cube. Our cube.js. So I mentioned a quad function, which we haven't really talked about yet. This is basically just a handy dandy function for defining a quad or a square-ish, rectangular-ish object. And it's just setting up vertices for that. So here you see function quad push down a vertex array. But this nice 3D rotating cube that you see here, the only real difference is that now we have axes and we have theta values for each axis. So we're rotating about some axis based on some theta. You kind of see I'm clicking rotate X, rotate Y, rotate Z. We have callback functions for these events. Anytime we click something, we are changing the current axis and just updating theta for that axis. But the tricky part, our vertex shader is now doing stuff. Fragment shader, still pass through. Nothing crazy. Vertex shader. I'm going to do some calculations. We're going to create some 4D matrices. Our X, our Y, our Z. Our position, RZ times RY times RX times V position. Okay, so this is what we are getting to with all these matrices. And if you look at this very carefully, you're going to see these formulas that we talked about a few moments ago in our slides. So C.x is the X value of cosine angles. And if we remember, we can index into array or into matrices .x, .y, .z. So that's a nice little shortcut, C.x. Here's vec3c. C.x would just be that first parameter. But there are our formulas. And we're seeing rotation happen. If I wanted this thing to translate, I would define some translation matrices that look like this, except they would be defined with that translation matrix construct, and we throw in a multiplication in here as well. Extra multiplications happening. Alrighty, any remaining questions? Otherwise, I will see you all next week, Tuesday. I will send out an announcement tomorrow with some more exam details, just so that it's fresh in your memory for how to do it and how to access it and all that. But other than that, good luck. If you are struggling or have questions on the exam, please feel free to ask. Yeah. Yep. Okay, so we have a double buffering question in Discord. Okay, so what's your question? Mm-hmm. Okay, so do you just want to, does anybody want to take a guess at the buffer flip? We got 1 minute left. I guess, yeah, sorry, go ahead. Don't mean to keep cutting you off. Yep. Yeah, I guess basically the simple answer is that anytime you are doing something in WebGL, you're rendering to a buffer that is not visible. So the buffer flip takes the back buffer and makes it the front buffer, which is what is displayed. Yep, and request anim frame makes that happen. Yep. Yep, sounds good. All right, other than that, I'm going to end the stream. And Chris, if you want to hang out in the voice chat, you can show me what you got going on. Other than that, good luck on Thursday, everybody. I will see you then. Bye for now.